Settled in the pleasant city of Geneva, Switzerland, the European Association for Atomic Exploration, generally referred to as CERN, remains a signal of logical investigation and disclosure. At the core of CERN's central goal lies the mission to comprehend the key constituents of matter, from the smallest particles to the huge grandiose field. One of the most exceptional logical tasks here is fixated on the enamoring story of the antimatter production line, where visionary scholars are extending the limits of human understanding and innovative ability. Antimatter, as we probably are aware, is at the core of a secret about why the universe exists by any means. So concentrating on antimatter is key to understanding our actual presence. Yet, in a journey to unwind one of the greatest astronomical secrets, CERN has found something strange occurring with antimatter that nobody can make sense of. This finding then leaves a hanging puzzle that scratches researchers' heads. So what precisely did they track down? Disturbingly, join us as we dig further into CERN's new disclosure that has the logical community bewildered. Antimatter seems like sci-fi, a material that looks like conventional matter but would release as much energy as a nuclear bomb if even a spot of it came into contact with anything around us. Little wonder that the researcher who first anticipated the presence of antimatter felt uncomfortable about what he had tracked down. These days, physicists are utilizing tremendous particle locators to test inconspicuous impacts that they trust will make sense of the focal history of antimatter. Where has everything gone? It is an inquiry whose arrangement lies in the absolute first moments of the Big Bang, nearly a long time ago. Something occurred in those days to turn a universe brought into the world with as much antimatter as standard matter into one peculiarly without the stuff. Did the antimatter disappear as the aftereffect of some abnormal peculiarity in the laws of nature? Or is it still out there, making up antimatter stars and circling around antimatter worlds? One thing is sure, in spite of its oddness and extraordinariness, antimatter is for real. The first traces of antimatter's presence arose in 1928 when 26-year-old English physicist Paul Dirac reported his disclosure of a solitary condition binding together no less than three of the critical hypotheses of material science: quantum hypothesis, electromagnetism, and Einstein's unique hypothesis of relativity. Dirac's condition had not one but two arrangements, one of them portraying the properties of the electron and the other foreseeing a perfect representation molecule with the same mass but inverse charge, the positron. Physicist Carl Anderson's disclosure of the positron in 1932 affirmed Dirac's forecast and highlighted the secret of antimatter. While electrons are pervasive, it took a cutting-edge particle indicator to find even a solitary positron. There was nothing in Dirac's condition or in the known laws of material science to make sense of why the universe ought to favor matter over antimatter. One idea was that the Earth just ended up lying in a relatively antimatter-free area of the universe. Maybe there were entire stars made out of the stuff sneaking out there. Provided that this is true, it would be adequately simple to tell, for as soon as antimatter comes into contact with conventional matter, it is completely obliterated in an enormous eruption of radiation. Einstein's renowned condition, equals 2 equals mc 2, shows that if just a solitary gram of antimatter comes into contact with conventional matter, the energy delivered is equivalent to the explosion of a nuclear bomb. Indeed, matter-antimatter annihilation is the most powerful source of energy in the universe, and its belongings are hard to miss. So, on the off chance that there truly are antimatter stars or even entire antimatter galaxies beyond our own, the Earth ought to be washed in a consistent gleam of gamma radiation, the indication of antimatter destruction. The truth could scarcely be more unique. Since the early 1960s, astrophysicists have sent increasingly complex gamma-ray detectors above the protective cover of the air to see what is out there. The message has been steady. There are no indications of antimatter objects anywhere in the universe. The absence of gamma rays from our own galaxy suggests that the closest antimatter star should be no less than 10 light-years away, with no more than one star in 10,000 being produced using antimatter. On a bigger scale, the shortfall of antimatter is even more striking. The degree of gamma rays coming from far-off galaxies suggests that something like 1 part in 100,000 of extragalactic matter can be antimatter. Yet, for what reason is there more matter than antimatter? Something occurred during the Big Bang to dispose of antimatter while leaving enough conventional matter behind to make the universe's stars and us. The first traces of what that something may be arose in 1964 when American physicists studying supposed K-meson particles found a peculiar impact called charge parity, CP infringement. This meant that antimatter doesn't always perfectly reflect the properties of conventional matter. The degree of CP infringement identified was tiny, but in 1967, the brilliant Soviet physicist Andrei Sakharov showed that it might very well make sense of why matter made in the Big Bang didn't match off precisely with all the antimatter. Two central questions loomed over Sakharov's idea. First, to have any chance of making sense of the secret of antimatter, CP infringement had to apply to something beyond K-mesons. Second, regardless of whether it applied to all particles, the effect must be strong enough to make sense of the colossal prevalence of matter over antimatter that we see today. Physicists are presently examining both these inquiries in immense machines that endeavor to reproduce conditions in the early universe. At Stanford University, California, the 1,200-ton Bobber particle detector is being utilized to concentrate on the impacts of smashing together electrons and positrons with a violence unheard of since moments after the Big Bang. The crashes produce unstable particles called B-mesons and their antimatter partners, whose decay can be studied for indications of CP infringement. In 2001, researchers working at Bobber and also at Bell, a comparable experiment located in Japan, reported that they had succeeded in detecting CP infringement among B-mesons and their antiparticles, thus showing that the effect isn't restricted to one kind of particle. Better still, the degree of CP infringement was right in accordance with theoretical computations based on the so-called Standard Model, the best theory presently available for understanding subatomic particles. The bad news was that the observed level was far below that required to make sense of the observed majority of matter over antimatter in our universe. Physicists are taking this as a sign that the Standard Model is inadequate with regard to something critical. Exactly what it might be remains unclear, but tests are already underway to figure it out. Astronomy and particle physics are often dismissed as being completely superfluous to daily life. Yet, by endeavoring to make sense of how antimatter missed out to matter in the birth of the universe, they hold the key to understanding our very existence. That is also why physicists at CERN are looking for subtle ways that antimatter differs from matter. Roundabout measurements of the impact of gravity on antimatter suggest that matter and antimatter both respond similarly to gravity. However, the difficulties of working with antimatter meant that a direct observation of antimatter falling freely under Earth's gravity had not been made. While antimatter can be made in the lab, it will annihilate upon contact with matter in a trial device, so great care must be taken to accumulate sufficient antimatter to perform an experiment. Over the past 20 years, researchers from the Alpha Group have been gathering antimatter at CERN, siphoning high-energy antiprotons from collisions in the CERN proton synchrotron and slowing them from the speed of light to velocities of a couple of hundred feet per second and a temperature of around 15 degrees above absolute zero. The antiprotons are then mixed with a cloud of positrons, produced by the decay of radioactive sodium, in a purported mixing trap controlled by electric fields. Ordinary hydrogen, the simplest and most plentiful element in the universe, comprises a positively charged proton surrounded by a negatively charged electron. The alpha experiment results in a few atoms of antihydrogen, where the nucleus is an antiproton and a positron orbits it. In 2002, Dr. H. revealed that these antihydrogen molecules transmitted and absorbed light at the same frequencies and wavelengths as ordinary hydrogen, just as Einstein would have anticipated. Since then, many experiments have roundaboutly suggested that antimatter also floats freely. However, those experiments have not been convincing because gravity is less than 1/1,000,000th as strong as the electromagnetic fields used to control the antiatoms. In the latest experiment, the antihydrogen particles were bound by a magnetic field inside a 10-inch long metal container. Since, like hydrogen, antihydrogen particles carry a slight magnetic field of their own, they can be held in place and kept from contacting the walls of the container and annihilating. The alpha team cooled the container and its antiatoms to within a fraction of a degree of absolute zero, draining them of energy and slowing them down. Then, the researchers turned off the magnetic field, and the antiatoms, freed from confinement, exited the container. A cloud of ordinary hydrogen atoms was dropped from the same height. Assuming that gravity influences matter and antimatter the same way, the two kinds of atoms should fall the same distance. This was the outcome they found. "We were all astounded," stated Dr. Farr. the trial pioneer and physicist at Simon Fraser University in Canada. Not a single one of us anticipated to see no difference between matter and antimatter. This was a perfect experiment, he added. If there had been an anomaly, we would have seen it, and there were none. However, as Albert Einstein said, no amount of experimentation can ever prove that you are right. The result, of course, does not prove that Einstein is right, nor does it make sense of the imbalance between matter and antimatter. Anyway, the researchers' minds were stirred because just last year Fermilab physicists revealed possible evidence that muons, a heavier and unstable cousin of the electron, are more sensitive to gravity than expected. Even if the result was a clear confirmation of Einstein's theory, the work would have been worth it, said Dr. Scher, who has spent his life studying antimatter. What makes antimatter so fascinating and baffling is that it acts exactly like matter, he said. It's impossible to explain to us why we live in a universe made of matter. We don't know, he added. The fact that the universe chose this way rather than any other way is one of the great secrets. Let's break this down into a more digestible explanation about CERN's work with antimatter, the secrets surrounding it, and recent revelations. Antimatter and its secrets. What is antimatter? Antiparticles. Each particle of matter has an antiparticle with the same mass but inverse charge. For instance, the electron's antiparticle is the positron. Dirac's hypothesis in 1928 predicted antimatter. He found that his equations describing electrons also had solutions suggesting particles identical to electrons but with a positive charge. These were positrons, discovered later in 1932. The imbalance issue. Theory of the universe's origin. According to the theory, the universe should have produced equal amounts of matter and antimatter. Yet, we observe a universe filled with matter and very little antimatter. This is a mystery. CERN's antimatter factory. How does CERN produce antimatter? Molecule colliders at CERN create antimatter through high-energy collisions in particle accelerators like the Large Hadron Collider, LHC. Antiprotons are very energetic and must be slowed down using a series of decelerators to reduce their speed to manageable levels. The slowed antiprotons are then combined with positrons, anti-electrons, to form anti-hydrogen atoms. Anti-hydrogen atoms are trapped using magnetic fields in a device called a magnetic trap to prevent them from coming into contact with matter, which would cause annihilation. Key revelations and investigations. Gravity effect. One of the secrets researchers are attempting to tackle is what gravity does to antimatter. Do antimatter and matter fall at the same rate? This is being tested at CERN. CP violation. CP violation is a phenomenon where the laws of physics apply differently to particles and antiparticles. This could explain the matter-antimatter imbalance, but so far, the observed effects are too small to account for the imbalance. Recent experiments. Researchers have been able to measure the effect of gravity on antihydrogen atoms. They use magnetic fields to suspend the antiparticles and see how they behave when these fields are turned off. Preliminary results suggest that antimatter responds to gravity similarly to matter, but these trials are ongoing to confirm these observations. Implications. Understanding why there is more matter than antimatter helps us grasp fundamental aspects of the universe's creation and evolution. Additionally, breakthroughs in antimatter could lead to advancements in energy production and potentially new technologies for space travel. Overall, CERN's work with antimatter aims to address some of the most significant secrets about the universe's structure and the fundamental laws of physics. While they have made substantial progress, many questions remain, driving further investigation and discovery.